Welcome to Savi YouTube channel created by Sai Vidya Institute of Technology, Bangalore. In this session, let us start a new theorem, that is Millman's theorem. And in this session, let us prove this theorem. Now, let us discuss what is the importance of this theorem and what is the statement of this theorem. Suppose if you are having n number of voltage sources connected in parallel. For example, this is one practical voltage source, another practical voltage source, like this. If n number of voltage sources with their internal resistances or impedances connected in parallel across any two terminals, then this entire network can be replaced by a single voltage source in series with a single impedance by using this theorem. Then you can ask, what is the speciality of this theorem? See, when you want to convert n number of voltage sources into single voltage source, then what is the procedure you should follow if you don't know this theorem is, you have to convert each voltage source into equivalent current source. Then you will get n number of current sources in parallel. Then those current sources you have to make it into single current source in parallel with a single resistance or impedance. Then you have to convert that current source into voltage source to get a single voltage source. That is what the procedure we have followed in a source transformation technique. But when you are applying this theorem and when you are solving the problems on this theorem, then you no need to convert each voltage source into equivalent current source to get a single voltage source. Just you have to make use of one simple formula obtained by the proof of this theorem to get a single voltage source. That is the advantage of this theorem. So, now what is the statement? So, what is the statement of this theorem? Any linear bilateral network, in any linear bilateral network, if n number of voltage sources with their internal impedances or resistances connected in parallel across any two terminals, then the entire network can be replaced by a single voltage source in series with a single impedance, where a single voltage source Vs is given by sigma k equal to 1 to n Ek Yk divided by sigma k equal to 1 to n Yk, and single series impedance Z is given by 1 divided by sigma k equal to 1 to n Yk. This is the statement of the theorem, where here E represents the number of voltage sources in the network which varies from 1 to n, and Y represents admittance of this network. For each voltage source, what is the admittance? So, that means E represents voltage source here, Y represents admittance of each voltage source. So, let us now prove this theorem by considering the same network. Okay? Now, let us prove this theorem. Okay. Proof. Consider n number of voltage sources E1, E2, E3, etc. n with their internal impedances Z1, Z2, Z3, etc. Zn are connected in parallel as shown in figure say A. Okay, I have considered this network to prove this theorem. Now, my intention is to convert this network into a single voltage source in series with a single impedance. Now, to prove the theorem, you do not have any option. you have to convert each voltage source into equivalent current source. Okay. Now let us convert each voltage source into equivalent current source. Okay. Now let us convert each voltage source into equivalent current source. So let us write here current source. A practical current source is represented by a current source in parallel with an impedance. Okay. I converted this voltage source into current source. What the arrow? Arrow should be right side for current source because positive is right side. Now I will take this current as I1, okay, in parallel with the same impedance Z1. Similarly, you convert this a current source in parallel with an impedance. Let this current be I2 and impedance is Z2. Again similarly convert this into current source. I3, let it be I3 in parallel with an impedance Z3, etc. Now this one, that is a current source IN, because this is EN, in parallel with an impedance Zn. Okay, it is connected across the terminals A and B. So I have converted each voltage source into equivalent current source, etc. and n number of voltage sources you have, hence I have shown n number of current sources. Now what is the value here? Here what is I1? What is I1? E1 by Z1. E1 by Z1. So what is I2? E2 by Z2. What is I3? So E3 by Z3. What is IN? En by Zn. Okay. Here I1 is equal to E1 by Z1, I2 is equal to E2 by Z2, I3 equal to E3 by Z3, In equal to En by Zn. Now, since n number of current sources are in parallel, definitely I can convert this complete network into single current source. So if you want to simplify the network, the current sources should be in parallel. Actually, voltage sources should be in series. Then only you can able to simplify that part of the network. So if voltage sources are in parallel, you cannot add or subtract the voltage values. That is why you are converting. If current sources are in parallel, you can add or subtract the current values depending upon the direction of current. Now all are in the same direction, I can add all the current values to make it into single current source. Now I can convert this into a single current source. Okay. Let this current be I in parallel with a single impedance Z. Okay. This is terminal A, this is terminal B. So I have converted this complete network into a single current source given by I in parallel with an impedance Z. Now what I should find? I have to find what is I and what is I Z. So now what is I here? I is equal to summation of all the currents because the direction is same. So I1 plus I2 plus I3 etc. In. So I is equal to what is I1? Substitute here. E1 by Z1 plus E2 by Z2 plus E3 by Z3 plus etc. En by Zn. Okay. Now I is equal to 1 by Z. Inverse of impedance is admittance. Hence I can write inverse of Z is equal to admittance, that is Y. That is Y is equal to 1 by Z. You know that. Admittance is inverse of impedance. That's why I can write here E1 into Y1. 1 by Z1 I am taking it as Y1 plus E2 y2 plus e3 y3 etc. en yn yn. Now I is equal to this, I can express in summation notation sigma k is equal to 1 to n ek yk. This is your I. So let this equation number 1. This is your I. Now what I should find? I should find the value of z. Now let us find the value of z. So how to find z? This z1, z2, z3 etc. zn, they are in parallel now. Therefore I can write 1 by z is equal to 1 by z1 plus 1 by z2 plus 1 by z3 etc. 1 by zn. Okay. So 1 by z is equal to 1 by z1, you know, y1, this is y2, this is y3 etc. yn. Okay. So 1 by z is equal to, this can be expressed in summation notation sigma k is equal to 1 to n yk, where k varies from 1 to n. Okay. This is your z. Now I want z now here, therefore z is equal to what? 1 divided by sigma k is equal to 1 to n yk. Let this equation number 2. Now I got the value of I got the value of z. Okay. Now finally what I want? I want to convert this into voltage source. No? Therefore I will convert this current source into equivalent voltage source. Now let us write what is the voltage source here. Okay. Now all of you observe here. Let us convert this into voltage source. A voltage source in series with an impedance. So right direction is right side, hence this should be positive, this should be negative. So this is what the voltage source Vs is equal to what? V is equal to what? I into Z now. Right here its value is I into Z in series with the same impedance, that is Z, across the terminals A and B. Okay. Converted this current source into voltage source. Now let us find this voltage source value. So since Vs is equal to I into Z, now substitute 1 and 2. So one is I, second one is Z. Now substitute 1 and 2. We get Vs is equal to what? I is what? Sigma k is equal to 1 to n ek yk into what is I? What is Z? 1 divided by sigma k is equal to 1 to n yk. This is your Vs and Z is anyhow same. Okay. Now I will rewrite this here properly. Let us rewrite it properly. That is given by single voltage source is given by, so this is in the numerator, that is sigma k is equal to 1 to n ek yk divided by sigma k is equal to 1 to n yk is your single voltage source value. Okay. That is you have converted the given network into a single voltage source. That single voltage source is given by this equation. And what is the series impedance? Series impedance is given by this equation. Now let us rewrite this. Okay, all of you observe here. That is, and single series impedance is given by Z is equal to 1 divided by sigma k is equal to n to n yk is your single series impedance. That is, you have converted the given network into single voltage source in series with an impedance. Since I have considered impedance, this can be or this may be an AC source. Okay, it can be DC source also, but since I have considered impedance, let it be AC. Now let us see how to make use of this formula. We have got some formula. Now let us see how to make use of this formula. So suppose, for example, if there are 3 AC voltage sources are in parallel. Assume that we have 3 AC voltage sources in parallel. I want to convert these 3 AC voltage sources into single voltage source. Then how to make use of this formula? Now, when there are 3 AC voltage sources, 3, then K becomes 3 here. So K is equal to 3. Then how to write this formula? Then single voltage source Vs can be written as E1 Y1 plus E2 Y2 plus E3 Y3, okay, E1 Y1 plus E2 Y2 plus E3 Y3, because K varies from 1 to 3 here, divided by Y1 plus Y2 plus Y3. That's all. It is so simple. What is here Y? Y1 is equal to what? 1 by Z1. Y2 equal to what? 1 by Z2. And Y3 is equal to 1 by Z3. And what is the impedance value? And Z is equal to 1 divided by, okay, Y1 plus Y2 plus Y3. Like that you can write the formula when the network is consisting of 3 AC voltage sources in parallel. Then you can easily obtain a single voltage source in series with a single impedance by using this formula. Just you are going to make use of the formula when you are solving the problems. So this will be given, voltage source values will be given and impedance values will be given. To find Y here, take the inverse of that, substitute, you get the value. Suppose if the network is having DC sources, okay, formula remains same. So for DC, what will be given here? Resistance will be given. Okay. Then if resistances are given, we will take the conductances. Conductance is represented by G. Then what will you get here? E1 G1 plus E2 G2 plus E3 G3 divided by G1 plus G2 plus G3. What is G represents? Conductance, inverse of resistance. That's all. Similarly, resistance you are going to find here, that is given by 1 divided by G1 plus G2 plus G3. Okay. Suppose if you want to write that also, I will just conclude that. So if the network consisting of 3 DC voltage sources in parallel, then according to Millman's theorem, the single voltage source value is given by Vs is equal to, what I should write? E1 G1 plus E2 G2 plus E3 G3 divided by G1 plus G2 plus G3. What is G here? Conductance. So here G1 is equal to 1 by R1, G2 is equal to 1 by R2, G3 is equal to 1 by R3. And next what you want? Resistance you want. Then resistance is given by 1 divided by, instead of Y you are going to write G. G1 plus G2 plus G3. That's all. So this theorem is so simple, proof is also very simple, solving the problems is also very simple. Just you are going to make use the formula. So, what they will give in the problems, so they may give either 3 voltage sources or 4 voltage sources, or they may give current sources also. Suppose if they give current sources, you have to convert that into voltage source. So, this Millman's theorem is applied only whenever voltage sources are in parallel. If any current sources are in parallel, you have to convert that into voltage source. So, only voltage sources should be there in the network and they should be in parallel. Then load may be given, some load will be given, then immediately you convert the n number of voltage sources given in the problem into a single voltage source in series with the impedance. Then if load is given, connect the load and find the current using Ohm's law. That is all. So, it is so simple, definitely you can follow this theorem very easily. So, in the next session, let us solve problems on Millman's theorem. Thank you one and all.